Hello, everyone. Thank you very much. What an amazing conference to be at. When I first got the confirmation that I'll be on the duck stage, I was like, the duck stage, that's interesting. Now I understand why. So amazing reference. Today, in the next 25 minutes, a little bit less than that, we're going to talk about eBPF. How many of you have heard about it before? OK, few hands. But yeah, it's a new thing. We're going to see what it actually means. And hopefully, by the end of the presentation, you probably have a good idea about what eBPF actually is. I skipped the boring part, the introduction, since that's already done. And hopefully, you can have next. No? OK. I skipped that. The first thing I want to mention is naming is hard. We know that in the software engineering, have you ever been stuck in a variable for more than 5 seconds trying to figure out what the naming is? But eBPF is one of those confusing names. And the reason why I got even interested in eBPF, I kept hearing about it in the cloud-native community. And I was commuting one day and then listening to a podcast. And in one of the episodes, the guest was Liz Rice, which is one of the very known faces in the cloud-native community. And the host asked Liz a very interesting question, very intriguing, actually. And he mentioned that eBPF is one, actually, of those technologies that everyone is talking about, but nobody really understands. So this presentation basically highlights the journey of trying to understand what eBPF actually is. The clicker decided to not work, so it should be fine. A little bit of history to understand what eBPF actually is. So it started with BPF, Berkeley package filter, that was introduced in a paper in '93, and it was basically a language that looks very similar to assembly language to handle packet filtering, to handle network packets. That's an example of how it works. So basically, that's an EP request or EP Ethernet packet that is coming in, and then if it's match a specific code, we drop the packet, otherwise we let it pass. Dropping here means that it should return 0, which means that we will not do request pass. And then if we return something different than 0, we should block it. So that was packet BPF. And then in '97, we started to get the first version of BPF, introduce it. 2012, we started to try to expand a little bit with CComp BPF, and introduce it into security. And then in 2014, someone, a group of community, decided to extend what we called actually eBPF. And where the naming came from, extended BPF, which is a way to make the kernel programmable. What is the relation between eBPF and BPF? Absolutely nothing. The eBPF has grown very much compared to the initial intention of BPF that was in '93. But within the Linux community, we still reference BPF sometimes, just to know that eBPF and eBPF within the Linux community, within the cloud-native community, means actually the exact same thing. So eBPF now is what used to be BPF. Naming is hard, I already mentioned that. And then I want you to start to understand what eBPF is. And eBPF is an important part within the Linux kernel. And then trying to understand what the Linux kernel actually does. So when we use our languages, we use a high-level programming language. So for everything that we need to do, allocate memory, handle a network package, talk to the drive and load a file, whatever, we call the kernel. And then there are some very specific protocols that we use in order to talk to the kernel. So the kernel does a lot of the heavy lifting on our side. So for example, if I use strace, which is a small utility function that enables me to track what's the calls that are made to the kernel for the smallest commands, like strace, like ls, for example, which is basically list the folders within a file, you can see that we performed a lot of options, a lot of calls to the Linux kernel in order to perform this ls, which we perform probably dozens, if not hundreds, during the day if you're using a Unix-based operating system. OpenAdd, for example, which is a system call, was executed more than 34 times. So there is a lot of heavy lifting, a lot of calls, a lot of back and forth that is happening with the Linux kernel in order to execute the smallest possible function or call. However, since the Linux kernel is an interesting piece, a very important piece of software engineering within the operating system, in order to add the functionality, we had historically only two ways. The first one is to add support to it, to the Linux kernel. And starting by writing a proposal, trying to convince the whole Linux community. And by the whole, I mean even Linus Torvald needs to be convinced by your proposal. And then you need to make the changes that you have, make the tests. And then once that merged and you manage to convince the whole community, then you can start using the Linux kernel. The problem is the Linux kernel versions that we use in our distributions are a couple of years old because Linux kernel or Linux distributions need to heavily test and thoroughly test the Linux kernel because as software, a critical piece of software engineering, the versions that we use are a couple of years back for the Linux kernel. So even if you manage to convince the whole community to add your feature, you need to wait a couple of years until you can do it, or you can basically backport it your own, and then you're going to be the last man standing supporting it until it goes mainstream. The second option we had is basically Linux modules. That's what we did. The option is basically building your own Linux module that you have to call unstable API within the Linux kernel that are not meant to be used within the public. Their functionalities are only used within the Linux kernel. And developing the Linux kernel, meaning that you have to develop it on your own, and that each Linux kernel versions may or may not introduce some breaking capabilities. And you have this kill loop where you, whenever there is a Linux kernel versions, you pray to someone in order to not have those breaking changes or making your life a little bit harder. So here it comes eBPF. And the idea here is to make the Linux kernel somewhat programmable. And it ensures that the code that we wrote is basically got loaded to the kernel at the same execution pattern with the same speed as it was written from the get-go from the Linux kernel. How is that? So there are frameworks, libraries, whatever, that enable us to write eBPF programs. eBPF programs have two components. The first one is user space code, and the second one is the kernel code. We're going to focus in this diagram on the kernel code. So you write your eBPF program in whatever language you want in the user space. However, in the kernel space, you are limited with C and Rust. Why is that? Because the kernel only supports those two languages. You will end up generally with C. So you write your C program, and then you compile your eBPF program into a bytecode. So that's not the end code that is going to get loaded to the kernel, but it's temporary state, similar to the Java language. Like you end up with a bytecode. And then you load that code, that bytecode, into the kernel. In the loading process, we have what we call the verifier. And the verifier here ensures that the program you run is actually the program that you're trying to run is actually safe to run. So the verifier does a lot of verification, well, as the name suggests, to ensure that the program is safe to run and it does not perform some malicious execute malicious code on your behalf. So it verifies that you have the right to execute the code. It verifies that the program that does not exist arbitrary memory code. It verifies that all the execution path of your code have an end stable state. If not, it will not allow you to pass this step. Once the verifier gives a thumbs up that you can run your program, then the next step is to JIT compile your code. Just-in-time compilation, which takes the bytecode and turns it into native code. And that's the important piece because it allows the program that you wrote to be similar somehow to as if it was written from the get-go to the kernel, and then you load that native code into the kernel. How it works? I have a small example for you, which is using BCC, which is a Python library that allows you to write eBPF programs. As you can see, we have some C program and another Python program. It's kind of a mix. Let me increase it a little bit. Too much. So the C program, that's what we call the kernel code. That's the code that gets loaded into the kernel. And everything else, you can forget about it. It's just like a way to load and execute the program within the kernel. So I'm specifying here what attachment point I want. I will get to that in a minute. And defining some metadata for my program, and then doing some printing debugging statements to my program. But the program is this one, and I'm simply saying print hello world. So if I execute this program, obviously Python 3, someone broke something, but that's fine. If I execute that program, since I'm listening to execv, which is a system call, I need to execute something. The moment I execute something, there is some process happening in my machine, in my virtual machine. Something execute like PS, ls, everything will basically generate hello world. The interesting part is, if I interrupt it, I can change the code and redeploy it again. So if I do hello info bip shift, yes, I can spell it right now, and reload it again. Hopefully it compiles correctly, and then print something, you can see that it changed. That is something that we are not used to in the Linux kernel. Because we used to have this long release cycle. Whenever we want to change something with the Linux kernel, we needed to wait for a few months or even years in order to get that new feature. So eBPF basically enables us to have this continuous feedback, continuous deployment, continuous development, continuous delivery within the Linux kernel. That's one of the big promises of eBPF. You can interact with the kernel. You can load programs in the kernel similar to what you use in your CI/CD pipeline or any languages that you use, which is one of the big promises. The first one and the second one is basically safety and security. It ensures that the program that you load to the kernel is actually safe to run. And why is that? Because the verifier has a lot of logic, a lot of checks in order to ensure that your program is actually safe to run. Even with that, you don't want someone to write your eBPF program on your behalf and load it into your Linux kernel. So you don't want to execute arbitrary eBPF programs on your kernel, because the kernel is still critical. But if you know the knowledge, you trust the code, the verifier might help you in there. It's standardized. Remember the Linux kernel module? The EPS that are provided for eBPF are actually stable to run and mean to be supported for years to come. Which is really good from a kernel development point of view. And finally, it's very efficient. So imagine running the code into the eBPF program that's executed within the Linux kernel. It's order of magnitude faster than writing the program to the user land. And you will see some examples of speed gain that we have. A little bit of the building blocks. I mentioned that when I want to load the eBPF program, I need to specify a type and attachment points. So there are dozens, probably more than that, program types that you can define within eBPF, depending if you want to have user pro program, kernel pro program, trace points, network, depending on what you handle within the Linux kernel. And there are also attachment points. An eBPF program type can have multiple attachment points. And those basically are events that you want to listen to. eBPF is an event-driven kind of architecture. The kernel, basically, when the event is triggered, it delegates the execution to your eBPF program. The naming is hard. eBPF program, and then return it to you back. What you can attach your program to, basically anything within the kernel stack. Since the kernel has visibility over everything, you can attach it to a program into user space. You can track the execution of a specific code of your program. You can attach it to the system calls, the execution of your program. You can attach it to when the file is open, when the file is actually closed, when you receive a network into your package. You can even offload it to NIC cards. You can offload it if the network interface, or you have a network interface that supports offloading programs. You can offload the execution of the programs to that network interface. So the eBPF program actually gets executed without it reaches your CPU, without reaching your kernel. So you are basically doing the filtering of the network packets, doing the load balancing before it even reaches your network packet. So it's off CPU kind of handling. eBPF maps, very briefly, when you write program, you need some data structure in order to share the data. eBPF maps are basically a way for eBPF programs to share the data. And it can they have different formats, like the normal data structure, arrays, hash tables, stack, use, whatever, you know it all. And then it enables two-way direction of sharing the data. The kernel program can write data to those eBPF maps, and then the userland program can read those data, or the userland program can share those data to the eBPF kernel, and then it can read from it. So these two directional ways of writing and reading enables to build robust systems, as we're going to see in a minute. And then helpers, since we're dealing with the kernel, we need some eBPF program does not know how to generate a random number, how to handle network packets, how to allocate some memory. So all of that is provided with some helper functions that are stable in the Linux kernel, specifically for eBPF, that enables you to handle those functionalities without need to worry about them. So those are basically APIs. You can think of them as utilities or helpers that enable you to perform functions without the need to worry about the implementation from a kernel perspective. So the use cases, what we can do with it. So we can do network optimizations. Since I mentioned that briefly, but since the network has visibility over everything, you can basically handle anything within the network stack. You can build load balancers. You can build filters. You can even offload some of the network handling into the network card if it supports eBPF offloading. So you gain a lot in performance. Tracing and profiling, one of the biggest use cases that we are using eBPF at currently. And Brendan Gregg, the name is mentioned there, wrote a very cool utility functions similar to Linux command lines that we use that are backed by eBPF. So you gain basically visibility over all what is executed within your eBPF stack. Very cool set of tools that I invite you to try out. Observability and monitoring. Another cool thing we can do with eBPF, since the kernel has visibility over everything, you can basically track the events that you want to listen to and you want to track. And it is good because monitoring within the kernel has a couple of visibilities. It is not intrusive because you're monitoring everything within the Linux kernel. You don't have to install this third-party tool that basically inspect and ingest all those information. The kernel has already those information, so you basically track them, store them into your eBPF map, and then there is another program within the user space that does the magic. So it's much more faster and less intrusive, and a little bit more secure. And talking about security, you can write eBPF program that tighten the security of your cluster, your node, or even your program. So you can put checks in your kernel that make sure that your program that your developer are executing is basically not executing only some specific privileges, which is really cool from a security point of view. How to start with eBPF programs? There are a couple of libraries here. As I mentioned, C is probably your preferred language. eBPF is one of them. BCC is one of the first, but it's mainly used for learning. It lacks a lot of features to make it production ready. The one I demoed, but it's still very good to learn what eBPF structure is and start with it. If you're a Go fan, there are a couple of tools, eBPF Go and eBPF Go. Those are some options, but basically they end up compiling to C code or generating C codes. And if you're Rust, since Linux kernel supports Rust now, you have a couple of options as well. eBPF Rust and Aya is one of my favorites. And I won't have the time to demo it today, but I have a full demo. I will link the I will link the repo in the end of the presentation. But it's like a whole load balancer demo one, obviously, that basically redirects traffic and load balance traffic between different kernels using Aya. So that's a cool thing to check out. Another limitation within the Linux, within eBPF that used to have is you saw that when I didn't mention it because of the time, but when you load eBPF program, what happens is you compile the code, you generate the bytecode, and then you load the code or that bytecode into the Linux kernel. The problem is everything needs to happen into the same kernel, in the same version. Otherwise, you compile in one version, you deploy in another version. The problem is you end up with a mismatch because some types, some Linux headers that were in the recent versions are missing in your production version. So that's an issue that has been the case for quite some time. And then BCC, the program I showed, solved it by compiling everything into the host machine. So it delegates the compilation and then the deployment into the host machine. To solve that issue, the eBPF folks created what we call core, which is compile once, run everywhere, similar to Java principle. And then they did a little bit of rewriting of the kernel. They added a couple of things, but the masterpiece is BTF, BPF type file, which basically keep track of the offset of the layout of the difference between different kernels. So it tracks basically the changes between different kernels, and then when you compile, generate that BTF that basically shows the offset. And then when we want to deploy, the kernel reads that file and knows which version and what to replace depending on the layout and the layers of your Linux kernel. So basically, core is enabling to have more flexibility to deploy over the Linux kernel. Whenever we're starting talking about eBPF, it has a lot of excitement within the cloud-native community. We started to, should we eBPify? What a hard name to pronounce. eBPify everything. Some of the things that you should avoid doing eBPF with is implementing everything that is CPU heavy on the kernel side, because that will basically defeat the purpose and basically make your machine even more slower. So everything that is CPU intensive, CPU heavy, it's rather be on the user land. And whenever you need something or have a good use case for eBPF, probably move it there. One of the interesting things that has been trending lately is switching to eBPF-based load balancing tools. And here, a blog post that was published by Cilium, where one of the clients switched from ePVS to load balancer-based XDP using eBPF. And you can see that the decrease in the amount of CPU and resources they need in order to run the same set or handle the same set of traffic. So with the right use case, eBPF is really beneficial. When it comes to eBPF, I believe, and a lot of people in the community believe, that we won't be writing a lot of eBPF code, but rather using a lot of the tools that uses eBPF. Some of the tools I already mentioned. It's BCC, that's a set of tools that offers you some profiling information from the Linux kernel by Brandon Geck. Katran is a XDP load balancer written in eBPF. It's an open source project from Facebook, now Meta. They open sourced it in 2018, and that helped to eBPF to explode in popularity since then. So any request that is going in or out from Meta, be it Instagram, WhatsApp, Facebook, you name it, is going through Katran. So it handles a lot of traffic and helps to showcase the powerfulness of eBPF. Cilium, another tool very known within the cloud-native community, is kind of a load balancer network optimizing tool that is based on eBPF. For the security, there are a couple of options that you can use. Falco, Tetragon, Calico. All of them are open source based on eBPF. It helps you to tighten your cloud-native infrastructure. And then for profiling observability, my favorite here is Pixie. It's more than a monitoring tool or a profiling tool. It does monitoring as well. But there is Periscope from Grafana and Parka as well. All of them are open source, I think, and good, but all of them based in eBPF. And the good thing is the overhead that they add is very minimal. It's 2% to your infrastructure, which is way less than what we used to do for traditional tools. For networking optimizations, this is what we have if you are using Kubernetes, container, blah, 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 a container-based infrastructure or cluster. So basically, this whole piece is actually repeated on the container management side and also when it reaches your container. With eBPF basically networking, you save a lot of latency. And that is really important if you have a latency-sensitive application. eBPF for Windows, just to mention that Windows folk are trying to implement the same thing in Windows, so you may or may not have that in the future. eBPF Foundation, just to mention that there's some big guys in there trying to steer the direction of eBPF. eBPF has changed the way we interact with the kernel, and we're kind of switching now to microkernels, have a standard small kernel that we can augment and enhance and implement missing functionalities using eBPF. So it's slowly trying to be the case. And also implementing hotfix. Remember CrowdStrike? That happens on Windows. If Windows had eBPF, that couldn't happen in the first case, but we could have also implemented small patch using eBPF if that was the case. So implementing hotfixes in the kernel, zero-day vulnerabilities as we know them, can be really beneficial using eBPF. That was it. I'm a little bit over time, but I think I'm OK. Those are the resources as promised. And yeah.